Swayam Prabha. Digital India. Educated India.
Welcome to the 21st lecture in mechanics of materials. The last lecture we saw how to compute the shear stresses in shear stresses due to bending. Okay. In particular, we saw that the sigma xy shear stress could be computed from the expression Vy equal to sigma xy equal to Vy into Q divided by Izz into B, okay, where Q is nothing but the first moment about the neutral axis, okay. It is in particular given by y minus y naught into dA, okay. So, that we can write Q as Ys, where Ys is the centroid of the section area up to which we are interested in finding the shear stress, and As is the area of the cross section up to the point where we are interested in finding the shear stress. In particular, if you are interested in finding the shear stress at this blue cut, you have to consider the area above the blue cut from for As, and Ys would be the center of that area measured from the neutral axis location, okay, where this is at the neutral axis location, as origin of this coordinate system is at the neutral axis location, okay. So, now using this expression we found that for rectangular cross section the sigma xy will vary parabolically given by the expression here, and the maximum shear stress is 1.5 times the average shear stress in a rectangular section, okay, that is what we found. Now, let us go ahead and find what is the shear stress distribution in a I section. Here there are two issues. One is whether there will be a sigma xy shear stress that will develop or sigma xz shear stress that will develop in the I section. This depends upon the relative thickness of the flange to the relative thickness of the web, okay. So, basically now let us assume that the flange is thick enough that there can be a variation of sigma xy along the depth of the flange, okay. So, basically now what we are saying is we are considering this I section and we are interested in finding what will be the shear stress distribution on this I section, okay. Let us assume that the flange is of width Bf of thickness Tf and this I to be H, again this is of length Tf and the flange width is top flange is also of same width Bf, okay. Now, if I am interested in finding the shear stress at some location here, shear stress at some location given by that blue line cut, okay, then what I should do is I have to consider the area which is this area and the CG of that area which will be somewhere here, okay. So, let us assume that this section is at a distance y from the neutral axis location, okay. So, now then this distance would be, that distance would be h by 2 plus Tf minus y, okay, because h by 2 plus Tf would be the distance from here to the top of the top flange, okay. So, that will be that distance. So, your expression for sigma x y in the top flange would be Vy by Izz into, here the cross section width is Bf, because the blue line that cuts the cross section is of length Bf. So, the denominator is Bf, okay. The center of that cross sectional the shaded portion is given by Bf into h by 2 plus Tf minus y, that is area, into the centroid would be y plus h by 2 plus Tf minus y by 2, right, because that is the half of the distance is the center of that rectangular region. Okay, half of the depth of the rectangular region is the center of the rectangular region. So, what does this boil down to? This boil down to Vy by Izz, Bf cancels. So, I will be left with h by 2 plus Tf whole square minus y square by 2. Okay. So, what happens when y is equal to h by 2 to h by 2 plus Tf, that is at the top flange, top surface of the top flange, you can see that the sigma xy goes to 0 as required, and it has a parabolic variation through the thickness of the flange. So, if I were to plot the variation of this stress along the depth of the cross section, it will vary from 0 here to some value here at the bottom flange, bottom surface of the top flange, that will be y is equal to h by 2. When y is equal to h by 2, h by 2 sigma xy of the top flange is Vy by Izz into h square by 4 plus Tf square plus h into Tf minus h square by 4 by 2. So, that will be Vy by Izz into Tf by 2 to Tf plus h. Okay. So, that is the shear stress at the top of the flange, bottom surface of the top flange. Okay. So, this value is going to be Vy by Izz into Tf by 2 to h plus Tf. Okay. Now, what happens when I move on to the web? When I move on to the web, I have to take a section somewhere here. Okay. So, now I have to find the area that I have to consider is this entire area. This entire area I have to now consider for my computation of the AS and the center of the area YS. Okay. Now, let us find what is the expression for sigma xy of the web region. Okay. So, that will be Vy by Izz into, now the width of this cut is Tw. Let us assume that the web is of thickness Tw. So, the denominator is Tw. Now, area consists of two areas, one is the flange area which is Bf into Tf into its centroid. Okay. That centroid would be h by 2 plus Tf by 2, that will be the center of that flange, plus the center of this region, center of this region and area of this region is what I have to consider. Okay. So, that will be Tw into h by 2 minus y. Okay. And the center of that region would be y plus h by 2 minus y by 2. Okay. So, this gives me the expression for sigma xy of the web to be Vy by Izz into Bf by Tw into h plus Tf by 2 into Tf plus h by 2 the whole square minus y square. Okay. So, what happens when y is equal to h by 2? When y is equal to h by 2, sigma xy of web would be Vy by Izz into Bf by Tw into Tf into h plus Tf by 2. You find that this is nothing but Bf by Tw or sigma xy of top flange at the same interval, same section point. Okay. So, basically what happens is Bf is greater than Tw. So, this ratio is greater than 1 and hence what will happen is there will be a jump in the shear stress. Okay. So, basically there is a jump in the shear stress at that location. So, basically you will find that the shear stress increases from this value to some value Bf by Tw times, if this is tau 1, this will be tau 1. Okay. Okay. Now, where does the maximum shear stress occur in the web? Maximum shear stress occurs in the web at y equal to 0, that is at the neutral axis location. Okay. So, basically what we find is sigma xy web, maximum value of that would be at y equal to 0, that will be Vy by Izz into Bf by Tw, Tf h plus Tf by 2 plus h square by 4. Okay. So, that is the maximum value of the shear stress in the web. So, what happens is there is an additional term of h square by 4, okay, to whatever was contributing from the other flange web interface. Okay. So, this increases from here to some value here, that say that is tau 2. So, the variation is like this, and you can see from symmetry you will get it back like that, and this is something there. You will see now I am drawing this bottom portion of it, this will be tau 1, this point would be Bf by Tw into tau. Okay. Now, go back to the web and find what is the sigma xy of web at y is equal to minus h by 2. You will find that it will be same as this one was, it will be same as Bf by Tw into sigma xy of top flange. Okay. Now, the bottom flange you have to do the same thing as we did for the top flange, except that y is negative here. Okay. So, you will get a similar expression for the bottom flange also for sigma xy. Okay. There is nothing like top or bottom here, I could have done a section here like this and consider this area and done the same thing with respect to computation of sigma xy for the bottom flange. Okay. So, these two are having the same dimensions and hence you will get a stress distribution something like this given in this figure here. So, you will get a stress distribution something like this for the I section. Okay. The point to note here is at this section, that is at the bottom of the top flange or top of the bottom flange, there is a shear stress coming in here. Okay. You know very well that you are not applying a shear stress at this junction. Okay. there is a possibility of shear stress arising at the web flange interface because of continuity of the material, but there is no shear stress applied at the free surface of the bottom of the top flange. So, how will this tau 1 be resisted by the flange is the question. Okay. The flange is of sufficient thickness, then you can, and the web is of sufficient thickness that the overhanging portion of the flange is small, then you can assume that the tau 1 will be resisted by the flange. Okay. On the other hand, if I add a very thin walled section like hot rolled steel sections for I section, okay. So, then what will happen is the flange thickness will be like 10 mm or 12 mm or 20 mm at most. Okay. In those cases it cannot resist this tau 1. Okay. So, there should be a different mechanism by which there is a equilibrium satisfied by the sections. Okay.